Hello. We're going to continue our discussion of stoichiometry, this time looking at the limiting reaction of propane gas. Stoichiometry, if you recall, is a discipline of chemistry that involves balancing equations and determining the amount of reactants needed for a chemical reaction or the amount of products made from a chemical reaction. Limiting reactions are chemical reactions where one of the reactants are in limiting supply. The amount of that reactant is going to determine how much products are produced. Now pay attention, I did make some changes. Remember the Big Mac example for limiting reactions or ingredients. If I have 18 hamburger patties, 32 hamburger buns, 4 whole tomatoes, a head of lettuce, a jar of pickles contains 4 whole pickles, 100 slices of cheese, and a bottle of $1,000 dressing. How many Big Macs can you make? I'll give you a moment to look through your notes and put on your thinking cap. 18 Big Macs. Why? Because the hamburger patties in this case are the limiting number and are fewer than all the other components that make up a Big Mac. It's the hamburger patties that is a limiting ingredient in this situation. My focus today is using dimensional analysis to solve stoichiometry problems involving limiting reactants. In this lesson, we're going to apply what we have learned about using dimensional analysis and stoichiometry to solve the combustion of propane gas. This time, one of the reactants will be limiting. Recall that combustion reactions require oxygen, fuel, and heat. Our fuel is a hydrocarbon. Now, since we're doing this experiment on Earth, oxygen gas is in plentiful supply. However, if I was to do this experiment on the Moon or Mars, that would be a different situation. Recall that propane is a hydrocarbon that contains 3 carbon atoms and 8 hydrogen atoms. We're going to start with the balance equation for the combustion of propane, in which there is 1 mole of propane, 5 moles of oxygen gas. In the presence of heat, it's going to produce 3 moles of carbon dioxide and 4 moles of water. Chemists use the unit moles when talking about the amounts of molecules of gases. This is just a convenient way of talking about large numbers of molecules of atoms. Recall that the reactants are on the left side of the arrow. For the combustion of propane, the reactants are propane and the molecule oxygen. Heat is always required for combustion reactions. And the products are written on the right side of the arrow. For the combustion of any hydrocarbon, the products are always carbon dioxide and water. We will again use the what do I know method, writing down how many of each atom we have for both reactants and products. We're going to organize that in a 2 by n table for both reactants and products. Again, n is going to be 3 because we have 3 atoms, carbon, hydrogen, and oxygen. We'll also cross-multiply our molecules to balance the equation. Having set up our table, we see that when we start off with, we have 3 moles of carbon atoms for the reactants and products, 8 moles of hydrogen atoms for reactants and products, and 10 moles of oxygen atoms for reactants and products. This is a balanced equation. Now let's assume we have a small propane tank used for camping that contains 5 moles of propane. How much carbon dioxide will we produce if we burn the entire container of propane? If you notice our table, we now have 15 moles of carbon atoms on the reactants, 40 moles of hydrogen atoms on the reactants, and 10 moles of oxygen atoms remain. This is no longer a balanced equation. We will have to rebalance our chemical equation to determine the answer. Let's again start with the carbon. Carbon for the reactants are found only within the propane molecules. Each propane has 3 carbon atoms, and we have 5 moles of propane. 5 times 3 is 15, thus 15 moles of carbon. We start off with 3 moles of CO2, and that gives us 3 moles of carbon atoms. This is not balanced. What would you do to balance the reactants and products for carbon? If we multiply the carbon dioxide by 15 instead of 3, now we have 15 times 1, or 15 moles of carbon for the products, 15 on the reactants. Carbon is now in balance. But we now have 34 moles of oxygen atoms for the products. Now are you beginning to understand why we're going to do the oxygen last? But for now, let's move to the hydrogen atoms. We have 8 hydrogen atoms within 1 molecule of propane. There are 5 moles of propane. 5 times 8 is 40. So there's 40 moles of hydrogen atoms on the reactants. In our current equation, there's only 8 moles of hydrogen for the products. The hydrogen atoms are not balanced. What would you do to balance the hydrogen atoms? If we multiply the water molecules by 20 instead of 40, 20 times 2 is 40. That will give us 40 atoms of hydrogen for the products. Hydrogen atoms are now in balance as well as the carbon atoms. Now let's move to the oxygen atoms. As we notice, our oxygen atoms has increased again, this time to 50 moles. So let's check the oxygen atoms. Oxygen is only contained in the molecule oxygen gas on the reactant side. So only have to cross multiply or multiply that. It is not currently balanced, but what would you do to balance the oxygen? If I multiply the oxygen gas by 25 instead of 5, or 25 times 2 is 50, now I have 50 moles of oxygen atoms for the reactants and 50 moles of oxygen atoms for the products. The oxygen atoms are now in balance. Now let's go back and recheck our numbers. What do I know? There are 50 moles of carbon atoms for the reactant. There's also 50 moles of carbon atoms for the products. The carbons are balanced. There are 40 moles of hydrogen atoms for the reactants and 40 moles of hydrogen atoms for the products. The hydrogen atoms are balanced. There are 50 moles of oxygen atoms for the reactants, as well as 50 moles of oxygen atoms for the products. The oxygens are balanced. The chemical equation is now in balance. We will produce 15 moles of carbon dioxide gas. Congratulations! You have both balanced a combustion reaction involving propane and determined the amount of product made in a limiting reaction. This ends our discussion of stoichiometry for today. I'll bid you adieu, and I will ask you to just take care until we see each other again.